We are.
You are right, because I also did not start. Okay. Okay. So for first gradient continua, what we did? We have this deformation energy. Then we calculate the first variation of energy with this first step. Then you integrate by parts, and you get integral over C star of minus div of something dot delta key plus integral over the boundary of C star of dw df dot n everything dot delta key. Okay, so the deformation energy can be represented as something per unit volume dual of virtual displacement and something per unit surface dual the displacement. Lagrange gives a name to this something, and he calls it force per unit volume and force per unit surface. Okay. Now assume that you believe you are inductivist. Okay. And you believe to have an experiment in which you have forces per unit line. So you write Px equal something, forces per unit volume plus forces per unit surface, plus integral on a line of an external force per unit line. Okay, so you have that Px is something having this form, the old form, the form you have deduced with the first variation of deformation energy, plus the integral on a curve of Bx per unit line dot delta key. Okay, now what you can do? You can choose a small region sigma epsilon star around gamma star. So imagine that this is gamma star, and you on the boundary, and you take a small region around it. So you move this curve epsilon on one side, minus epsilon on the other side, and you write the principle of virtual work on this for a virtual displacement delta key, which is concentrated on this small stripe. What you get for every d concentrated on the stripe. Okay. So what you get? That for every delta key concentrated on the stripe, 0 is equal to the integral of this plus integral on the line. So when epsilon tends to 0, the integral of a surface integral tends to 0. So you get that the integral of Bxl dot delta key is equal to 0 for every delta key concentrated on the stripe. And this is the integral over gamma star. Now, we made 100 times the reasoning. We know that when this equality to 0 is true, Lagrange theorem that Bx is equal to 0. So we can conclude first gradient continua cannot support line forces. I mean, this is not an experimental fact. This is a mathematical fact. If your model is based on the assumption that the deformation energy depends on F only, then you cannot have in your model forces per unit line. Okay, so this is a logical fact. Okay. So in one gradient continua, no line forces are applicable to the body. Okay. Now, from the philosophical point of view, I mean, this happened very often in history of science. You know, some Greeks had a model of universe in which the stars were fixed. Some other stars were moving, and the sun was moving, and the earth was in the center of the universe. And they claimed that the law of physics, which are valid on the earth, are not valid in the stars. So they had a philosophy of science in which the law of physics dependent on the distance from the center of the earth. So in the center of the earth, you have a certain law of physics. When you are on the surface of the earth, you have another law of physics, and so on. So when Galileo, using a telescope, could show a movement on the surface of the sun, okay, which was suggesting that sun was a kind of liquid or, you know, a fluid moving. So he was denying the fact that the law of physics in the sun were different from the law of physics on the earth. Some Jesuits told him that it was not the sun which was showing some spots. It was the telescope which was wrong and not working in an appropriate way. Okay, so usually what can happen? That the healthy thing is that you accept that Cauchy continuum model only that Cauchy continua can model only a limited class of phenomena. So Cauchy continuum theory is limited to a particular class of phenomena, which is very healthy. I say, okay, for me, okay. Or you believe that Cauchy continua coincide with reality. In case one, you look for more general models. In case two, you decide that line forces cannot exist, which is like denying, like Jesuits denying the existence of solar spots. Okay. So this is the end of the example which I wanted to give you, the first example in which with which we interrupted our flow of reasonings. Okay. Now I want to show you another simple result. We already spoke about this, but I want to repeat it for you another time. So I want to tell you that Piola theorem is valid for one first gradient continuum. I tell you now what is Piola theorem. I will tell you at the end. So let us follow Piola's reasoning. Okay. For every virtual displacement, this is the principle of virtual work. For every displacement, the first variation of deformation energy plus the external power on the virtual displacement has to be equal to 0. Okay? Now, if this is true for every displacement, virtual displacement, this is true also in the particular case of rigid body infinitesimal displacement, which we calculated many times. Okay? So the displacement delta key rigid is equal to the displacement delta key x0 plus delta theta vector x small x, the position of capital X, minus small x, the position of capital X0. Okay? So, first observation. Delta deformation energy calculated on delta key R is equal to 0. If you remember, I did all calculations. This is very easy to accept because there is no deformation in a rigid displacement. So we have chosen, in a sense, we must choose EDF such that this is true. Okay. When you have a good deformation energy, its variation under a small rigid displacement has to be 0. Because if you don't deform, if you are not changing the deformation state of your body, and a rigid displacement is doing this, then the deformation energy should not change. So in a sense, this one is a requirement for deformation energy. Okay? Then we have seen that Px has to be equal to this, an external volume force plus an external surface force. Okay? So if you choose delta key equal delta key rigid, look, I told you this 100 times. If something is true for every displacement, then this is true for a specific displacement. This is basic logics. Okay? So I'm not doing any particular case. I'm not developing the theory of rigid bodies. If you have a deformable body in equilibrium, it must have the first variation of energy plus first variation of external work, the external work of external forces has to be equal to 0 for every displacement starting from equilibrium. If it is rigid or if it is not rigid, this is true. Okay? So we choose the rigid displacement as a particular small variation of placement. This is equal to 0. So we know that the external work is equal to 0 for every rigid displacement. Okay? So you write integral over C star of bxv dot rigid displacement plus integral on the boundary of C star of surface forces dot the same rigid displacement has to be equal to 0. So as rigid displacement are parameterized with translations and rotations, so this has to be equal to 0 for every translation and for every rotation. So for every rotation and for every translation, I have rearranged this expression. So you have integral over C star of bxv dot delta kx0 plus this integral for every delta theta, okay, plus the surface integral of bx sigma displacement plus delta theta, so rotation, okay? So this is the same formula as I've written here, but I have started splitting the volume integrals.
Professor,
Okay?
Professor,
Yes.
may
Yes.
you keep that page for a while, please?
Yes. Yes.
Okay.
I keep this for a while. Okay. So this is the particular case of principle of virtual work valid for rigid virtual displacements. Okay. Okay. So if I have that a property is valid for every displacement, then this property is valid for a specific set of displacements. So you already understand that we are proving a necessary condition for equilibrium, not a sufficient condition. Because equilibrium occurs if and only if the work is equal, the total work is 0 for every displacement. And now we are considering the particular case where the virtual displacement is rigid. So one cannot expect that the final result which we are going to obtain is also sufficient for equilibrium. It is necessary for equilibrium. Can I move now?
Yes, Professor, sure. Thank you.
Okay. Okay. Now I will go slowly. We assume that delta theta is 0. The previous equality becomes this very particular equality because everywhere where we add delta theta, we place 0. So we are left only with these two integrals. And the sum of these two integrals has to be 0 for every delta key 0. So for every translation, if you want rigid translation. Okay. Okay. So if I can move, you remark that this delta key is independent of the integration variable. This is a fixed vector which can go out of integrals. Okay? So you get that the sum of these two integrals, inner product, every vector is equal to 0. Okay, which is the vector whose inner product with every vector is always equal to 0? The null vector. So we can formulate necessary condition for equilibrium. Balance of force, or as you can find in old books, equilibrium under translation condition. This is the condition of equilibrium under translation. Maybe it is clearer if we write condition of equilibrium under translation. Which you have learned by heart, because they hammered in your head the idea that it is evident. You know, who dares? I remember that when I tried to discuss with my professor of physics first year, I said, but why we are accepting this? If he was clever, he told me, look, we made many experiments and it is true. Those times I was naive, so I didn't dare to ask him, how do you measure forces? Because if you want to answer, I made many experiments and then I obtained this result. Okay, one must measure external forces per unit volume and per unit surface. Now, maybe you can think to measure forces per unit surface, pushing, okay? But how do you measure forces per unit volume inside a body? When somebody explains me this, then I will be able to maybe understand how you can deduce this with experiments. Okay, you can induce this with experiments. Okay. But another group was even worse. They told me that you are stupid if you don't see that this is obviously true. Now, what is amusing is that Piola and Lagrange felt the need of proving it, starting from the principle of minimum of energy. So this is not evident at all, because if Lagrange could not see it clearly, it means that this is not clear at all. We are simply accustomed. You know, they repeat us that balance of force is true, whatever force means. You know, I remember that I had a lot of pain as a student for understanding this. At the end, I learned it by heart. Okay. Now we have proven that it is a necessary condition for equilibrium. So if you accept minimum of energy as a criterion for equilibrium, you make some mathematical reasonings and you get this as a necessary condition. Okay, then we place this result inside the previous expression for virtual work equality where you have delta theta and delta key 0, and clearly you get this remaining equality. You have that for every delta theta, 0 is equal to bxv dot, this is the part of rigid virtual displacement relative to rotations, plus b sigma x dot this, which is the other part of virtual rotation. Okay? Now, I hope that you remember the property of tripole product of vectors. You know, this scalar is called tripole product of the three vectors constituting it. So you have bx, okay, delta theta, and x minus x0. So you can permute this equality here, following the arrows which have written there. The same you can do there, okay? And what you get, you get delta theta dot something, okay, plus delta theta dot something else. Now, why are we defining the moment of forces as we are defining it? So did you ask yourself, how, in English, you say that a definition comes out of the blue. Okay, so you fish it in the sky. Okay, in Italian, maybe in Neapolitan, we say that, how do you wake up one morning and without any reason you define something? Clearly, when you remark that delta theta is constant, so it can get out of the integral there. Okay? And you remark that this equality to 0 must be valid for every delta theta. You discover that this object here must be, of course, this object depends on x0. This object is to be defined. And we call this moment of applied forces, okay, of externally applied forces. And this moment has to be 0. Why? Because the condition of equilibrium under rotation implies this.
Professor.
Yes.
May I ask a question?
Yes.
What is the difference between when we wrote the equation, I mean the BV external and B epsilon external in the formula?
This one and that one.
Yeah.
This is a force per unit volume, and this is a force per unit surface.
Okay.
So in the drawing, if you can make a drawing. So if this is your body, you have forces applied inside the volume. These are B volume X. And you have forces per unit surface here. and these are Bx sigma. So Bx sigma is a generalization of pressure, while Bx volume is a generalization of weight, of the body. The weight is distributed in the volume and the pressure is concentrated on the surface. And we discovered that this is the most general, okay, we did it before. The most general external interaction for a first gradient Cauchy continuum must be of this form. So you have a volume force and a surface force, and only this. You cannot have line forces, as I said before. Okay. So these conditions can be only necessary. So the resultant force equals 0, and the moment resultant, the resultant moment depending on every pole is equal to 0. These are necessary conditions to equilibrium. They are not sufficient in general. Why? Because there is no information about internal deformation energy. So for proving them, you simply need to assume that internal deformation energy is 0 under rigid displacement. So this necessary condition cannot contain any information about the internal energy. Okay. Now, before we move, as we are having a very concentrated and difficult lecture today, I want to tell you, maybe I already told you, but I want to repeat you once more, the nice story by Professor Di Carlo. And, I'm becoming senile and I'm repeating every time. When I was young, I believed that old people repeating always the same thing were doing it because they are senile. Maybe this is true also for me now, I don't know. But what I want to tell you is that with experience, I understood that somebody, even Erden, who is very clever, okay, but even myself, I'm very clever, okay, somebody needs to have repeated the same ideas from different points of view before he digests them. Okay, so repeating is very useful. Some Latin word told was repetita juvant. Repeating things helps you. Okay. Now, I think it is very important to repeat the most important concepts, because this is the only way for mastering, for a student, for mastering them. I learned this during the university, then I repeated it in PhD. Then I went to France and I was obliged to teach these things 2 years in a row. Okay, so after the 5th time, while repeating my lecture at the blackboard, I stopped 2 minutes. French students believed that I was missing the word. Instead, I had a flash, and while telling them something, I understood everything I had repeated for many years. Okay, so you need to repeat many times, and I think that Di Carlo's nice example is very useful. A student wanted to solve the problem of deformation of a body using the concept of balance of force and balance of momenta only. Okay? So he claims that if you have a beam like this and you apply this force, so a force per unit line, or if you apply this force, a concentrated force, but the resultant of this system of force and the moment resultant of this force and the resultant of this force are the same, then the deformation of the beam is the same. Okay, so the belief of that student was, as we call equivalent to system of forces having the same resultant and the same moment, we say that they are equivalent. Then either I apply this or I apply that, then it is the same. Unfortunately, the difference of distribution of external forces and the deformability of the beam imply that this beam here is deformed in one way, and this beam there is deformed in another way. Okay, so calculating the total resultant force equal to 0 and the total resultant moment equal to 0 is not the same thing. Di Carlo explained this 10 times to a student. Okay, and he didn't pass 10 times the exam. 11th time I was present. So Di Carlo, being very upset, has drawn this picture. Erden, we must, citing the source, we must write this in our paper in a polite way. Okay? He said, you are a criminal, we are in middle age, and you are, here are horses, pulley, and you are in this, you know, this was a way for killing people during middle age. Okay? Now, this F1 and this F2, F1 is equal to minus F2. This is F3 and this is minus F3. The resultant force of this is equal to 0. The resultant moment of this is equal to 0. This system of force is equivalent to 0. So you should be happy to stay in that position. The student did not answer for 2 minutes. Then he had a moment of intelligence. And he said, I cannot be modeled as a rigid body. Okay? And he passed the exam. Di Carlo said, this man did not understand very much, but he understands enough for avoiding to do stupid things. Okay? So remember this. Equilibrium is obtained if you are in equilibrium, then the resultant force and the resultant moment are 0. But you may have a situation where resultant forces and resultant moments are 0 and you are not in equilibrium. Like this example, unforgettable, reminds you. So when you try to say that forces, balance of force and balance of moments are valid, think yourself in this situation and you will stop making stupid considerations like this one. Okay? Mathematically speaking, how can you characterize equilibrium without knowing the shape of internal force of in deformation energy. You cannot. Okay, so these may only be necessary conditions. Okay. Cauchy was not very stupid. He was indeed very clever. And this is the motivation for which he invented Cauchy cuts. Okay. So Cauchy not only studied the equilibrium of a body, he also introduced imaginary cuts. He was splitting the body in every possible sub-body, and he invented forces he called contact forces inside the body, and he postulated equilibrium for every sub-body. Okay? I think that we will need to clarify this point. We will do it later in this course before ending. But I'm sure that you have seen these Cauchy cuts in a class. So you more or less have an idea of the process of Cauchy. So he used equilibrium of forces and moments for every sub-body of the given body. Now, the bad news is that this process invented by Cauchy does not apply for second gradient continua. So, Cauchy invention of sub-bodies and equilibrium of sub-bodies is not valid for second gradient continua. Okay, Erden, this is another crucial point for our paper. Okay, so let us calculate. We will need hours. Okay, I don't believe that we will end this today. Okay, so let us calculate the first variation of deformation energy when W def is made of a function depending on f and on grad f. Okay, so now we proceed slowly to make long calculations. So you must be very patient, and I think that you will need to learn something more about divergence theorem. Okay, so we decided with Erden that we will stop before discussing about divergence theorem for surfaces. Okay. Okay, now the first variation of deformation energy is clearly, in our more general case, given by this. By the way, you will see that even if this procedure is lengthy, this procedure is giving us surely a result. Okay. Erden, in the preface of Lagrange book, it is written that the proposed procedure gives us a standard mathematical strategy for getting, with a uniform sequence of calculations, the final result without adding any assumption during the process. So we will need to cite this Lagrange statement somewhere in our paper. Okay, so please remember this. I know that you cannot read French. It is not your fault, poor boy. You know Turkish. What can we do? Okay. So, Erdem, Turkish people are never smiling when somebody is pulling their leg. You are serious. Okay. So let us calculate this first variation and let us write it with contravariant and covariant components. Now, this first addend already done. We did already. Okay, so I will not repeat the calculations. We will gather the results at the end of the process. Okay, so we have this second addend. Now, remark that Fi A comma B, or maybe let us be uniform, dFi over dFia dxb. We can call it FIAB with AB two indices for which symmetry is valid. Why? Because obviously you have this equality by definition, and we know Schwarz theorem, so the order of derivatives is not important. Changing the order of derivatives, you get the same result. So this animal here is symmetric with respect to any permutation of A and B index. Okay. Then we have this delta here. Okay. This delta here is a small variation of the second derivative of virtual displacement. Okay. Now, I know that this notation is very ambiguous. We will repeat some reasonings which we already did. Okay. So actually, I am wrong to write in this order. Let me write in this order. Okay. I consider that this is equal to that. So the second derivative of the small variation of placement is a small variation of the second derivative. Okay. And this equality is not obvious. So we need a space of functions which is rich enough to have second derivatives which are integrable and can be small. Not only, we want a space in which every small function has small second derivatives. Okay. So, very important, you need to be able to measure the smallness of second derivatives. Okay. When can we commute smallness with derivative? I mean, you write at least 20 pages in Lagrange textbook on this point. Lagrange was not a simple-minded mathematician, so he knew where dangers can be hidden. Okay. So he knew that we cannot commute smallness sine delta with derivative operator.
One I is missing in that equation, no? Next to W.
This is I, this is I.
Yeah,
Well,
in W there should be I, no?
no, why? W is a scalar.
Okay, okay.
So this is, W is an energy.
Yeah.
And this is the Lagrange Eulerian index for displacement.
Sorry.
So, okay, no, look, it is very important that you are following the structure of this equation because you must master it. So please ask all the time.
Yeah, I didn't see the chi has I, sorry.
Okay, by the way, I am losing sometimes the indices, so correct me when needed. Okay, so Lagrange knew that two functions whose value are close and whose derivatives are far can exist. Think about the first function here. Okay, we'll draw it in red. And the function in blue. Clearly, the function in red has very close values with the function in blue. But the derivative of the function in red is very different from the derivative of the function in blue. Okay. And so you are in troubles in general. Okay. So Lagrange knew that he had to choose a space for placements in such a way that delta and second derivative could be commuted. Okay. So the existence of these counter examples is the reason for which the space has to be studied carefully. The space of placements. Okay. Now, I want to remark for you here that Sobolev, a Soviet scientist, a very clever and inventive Soviet scientist, studied these spaces in 1940. But Lagrange used and Piola used them in between 1800 and 1840. Okay, so I decided that I can try to talk about these spaces in the way in which Lagrange and Piola did, and maybe only when some of you, hopefully many, will do PhD studies, I will ask them to invest some time for understanding Sobolev spaces. Okay, so I think that you can use these spaces, the spaces for which this delta can go out of the derivative in an intuitive way without knowing all the details of mathematical theory. We have here a mathematician. I don't know if he studied Sobolev spaces. If yes, he will have his life much easier. Okay. Okay. So let us now focus on one addend. So I called the new addend of the, okay, this is delta. Okay, you see, I find always formulas with mistakes. So I have called the second addend here in this first variation, I've called delta E double bar at the top. Okay. Okay, now this first variation here, we can integrate by parts, gathering one derivative here inside a bracket and integrating by parts with respect to this partial derivative. So this is nothing new when compared with the integration by part, which we already did. I will try to move this a little bit on the right if I manage. Okay, so I didn't calculate in the right way the space. So this is equal, and here I have delta xb, delta ki. Okay, so this derivative of this product gives us this term plus this term. So this equality is valid if we place minus there. This is the standard trick of integration by parts. Okay? Very well. Now, remark that this term, so please be careful, copy this equation, look at them, because for the next 3 lectures at least, we will need to work with these formulas. And this is very important for generalizing Cauchy continuum mechanics. Okay? So to understand why balance of forces and balance of moments is not sufficient for describing equilibrium. So be very careful in this. I will go very slowly. So this term here is similar to this term, which we already studied. So simply replace dw over dFi with minus d over dxa dw dFi. Okay. So if you call capital P bar IB equal dw over dFi minus d over dxa dw over dFiAB. So remark that this A is saturated there, and you repeat the calculations which we have done for the first gradient, you get the same result with the new P. Okay, so one could believe that nothing is happening. This is not true. Okay, so we can call this generalized Piola tensor. Why generalized? Because this is to be used in, okay, generalized to second gradient continua. Okay, many scholars believed that this argument was ending any discussion and that everything was done. Okay, we have a bad news or a good news, because, okay, look, Erden, we are crazy. You traveled up to Berkeley for learning new science. We want to discover something new, right? So it is a good news that you need to invent new techniques, right? So we are left with this term here, okay? We apply divergence theorem, Okay, we will go back to divergence theorem in few minutes, but this is d over dxa, and here you have the index A, okay? So we have a structure like that. If VA is this animal, okay? So in a sense, what is inside these brackets is a Lagrangian vector, okay? Erden, please try to repeat this with all the students, not only with Turkish students, okay? Because repeating will be very useful for you and for them, okay? There is a lot of space left for original research in this field. Everything you have written, you find written in the books of continuum mechanics must be modified in the framework of second gradient materials. Okay, so there are books to be written. This is a Lagrangian vector because this index is saturated, this B is saturated. Okay, so from the mathematical point of view, you have only a vector, a Lagrangian vector, and you apply divergence theorem to this Lagrangian vector. Okay, so the rule for applying, Gauss theorem, divergence theorem, the rule is replace this derivative with NA and replace the volume with the boundary. So this is the rule which has to be used for applying divergence theorem. We will come back to this point soon. So you can transform this integral into a surface integral, which is this one. Okay, this is a flux. You have the normal n is orthogonal to the boundary of C star. Okay. You have a flux and you have this VA vector whose flux is calculated on the boundary. Okay. Okay, but now this VA vector must be split. Why? It has to be split because inside VA you have the derivative of the virtual displacement. Okay, and we have learned that we must write equations for every delta key for finding equilibrium conditions. Okay, so we must isolate the delta key factor in our expressions. Okay, now I introduce a trick. For the moment, it is an algebraic trick. So from this equation here, look, you have saturation of B and B here. So what I'm writing, I am saturating B and B, C and C. So C is a new index, and delta is a Kronecker delta. Okay, so it is 1 when C is equal to B, and it is 0 when C is different from B. Okay, so I have not done anything new. So this expression here is exactly equal to this expression here. Okay. Now I stop a moment and I go here to describe what is happening geometrically. So we will do very slowly some reasonings. Then we will come back to this formula, okay? So take a vector VB, delta CB, VB, by definition of Kronecker delta, is equal to X VC, okay? So this is the identity. Okay, now I want to split this identity in a particular way. So let us consider the surface boundary of C star. This is boundary of C star. You have a vector V, and clearly you can project this vector V along the normal to the surface or in the tangent plane of the surface. Okay, so PV is parallel to the tangent plane to delta C star, and QV is parallel to N, to the normal of boundary of C star. And by definition of projections, PV plus QV is equal V, because the sum of this projection plus that projection gives exactly V. So this is understandable, clear, is based on geometry, okay? Okay. Now, remember that like every projector, if you apply P to PV, so if you take V, you project it, and then you apply another time the projector, you get again PV. So P square V is equal to PV. Okay. And similarly, Q square V, which is Q applied to QV, is equal to QV. This is true for every project. So I hope that this is easy for everybody. Okay. Now, this equality here, okay, this is true because the space where the boundary of C star is three-dimensional, the tangent plane is bidimensional, and the normal direction is one-dimensional, so that you have 3 dimensions, 2 from the tangent plane and 1 from the normal. So this equality, I mean, P and Q are enough for reconstructing V via its projections. This is the basis of Cartesian geometry. Okay, in a Cartesian system, you have 3 components for every vectors. If the space is three-dimensional, the tangent plane has 2 dimensions. The normal gives you the 3rd dimension. So this equality is true. So the identity can be reconstructed with the component of the projection in the tangent plane and the component of the projection in the orthogonal direction. We call PCB and QCB these components. Okay, now maybe it is good to say that P alpha V plus W is equal alpha PV plus PW. A projector is linear. Okay? So you can represent P with a matrix in our Cartesian coordinate system, and PCB and QCB are the matrices representing these projections. Okay? Okay. So we have that this was at the beginning delta E double bar def. This term is similar to something which we have already studied. We define a generalized Piola tensor, and we are left with this addend here, which becomes this addend with delta, and then you decompose delta as P plus Q. Okay? So we call delta epsilon triple bar this integral. Remark, this is on the surface. Okay? So we are left, and this is the big problem, and this is the novelty. This is the first time where you have an expression for a work which is given by an integral on a surface, but you have the derivative of the virtual displacement. Up to now, we met only delta Ki on the surface. Now we have the derivative of delta Ki on the surface. Okay? So clearly, we can decompose P plus Q, and we get two terms. We have this term with the QC projector and PCB with the d over dxc. This is a tangent gradient. So in a sense, which we must now understand, this is a normal gradient, and this is a tangent gradient. So up to now, I have not done anything else than decomposing the gradient into its tangent part and its normal part. Okay? Okay, here I have written something wrong. So maybe I move this thing down. So you know what I do? I cut this away. Okay, I will copy it here. And this should be dw, and this is P, C, d over delta Ki x c. Okay. Okay, so up to now we have done this decomposition. Now, let us go back to our Q. Okay. I hope that you have enough linear algebra behind you. Otherwise, you will need to reconstruct a little bit these steps. Q of a vector v is the projection of the vector v along the normal n. So you have v dot n. This is by definition QV. Okay. So what is QCB? QCB is NC and B, a dyad. You know, sometimes you will find this symbol, a dyadic product. Okay, so let us prove that the matrix QCB is NC and B. I hope that you agree with this. This is the definition of projection. Okay, so QCBVB is, if we are right, NC and B VB. This is V dot N, and this is NC, the C component of the normal. So if you multiply this times the basis capital EC, NC EC is equal N. Okay, so you obtain that this representation is true. Okay, so Q, the projection along N, sometimes you find this symbol, which is equivalent to this representation. Okay, so QCB is given by NC and B. Okay. So following the suggestion of Erden, I am very slow in telling you this thing, because even if these things should be known to you, you may find it difficult, as this is one ingredient of a very complex argument. It is better if you follow it slowly. Okay. Now I remember that one of the two addends of our d epsilon triple bar def is this one. And in this term, we have QCB d over dx c delta ki. So I copy this here. Okay. I replace QCB with NC and B. Okay. And I discover that maybe I can move this NC. Nothing changes if I place it there. And this is the gradient of Ki in the direction of N. Okay. So this is gradient of delta Ki dot N and V. So what I do? I replace this QCB d over dx c delta Ki with the new representation, and this is delta E triple bar deformation.
Why, Professor, why did we call the delta 3 bar? Because of the volume, or?
No, the 3 bar is the third addend in our decomposition.
Okay, okay.
Okay. So here we have only surface integrals. Everything concerns only surface integrals. Okay. Now, What is this? You will discover that this is a completely new term which we will need to study. So this is dW over dFIAB, and you saturate NA and B. So this is a quadratic function of the normal. And here you have a left index I. Okay, so this is a Lagrangian Eulerian vector VI. Okay, and you have that the normal derivative of the virtual displacement must be saturated with this VI in our expression. Okay. Here you have integral on the boundary of C star of NA dW over dFIAB P C B d over dx C delta Ki. What is this? We can call this a kind of parallel gradient of delta Ki, because only the derivatives along the tangent plane to the boundary delta C appear in this term. Okay, so we must, before ending this lecture, we must now understand something. No chance to integrate by parts this term. Why? Because you have VI, so V dot the normal derivative of delta Ki, and you have this inner product on the boundary. This is grad Ki dot n. So this gradient tells you how Ki is varying in the normal direction. So you cannot integrate by parts along the surface, because this gradient is telling you what is happening, which is the variation of grad Ki in the normal direction. So you cannot travel along the tangent plane for integrating by parts. So this is a term that cannot be integrated by parts. Okay, maybe it is worth to make a discussion like this. If I know delta Ki on the boundary, so delta Ki restricted on boundary of C star. So you know delta Ki here. Okay, this is the field delta Ki. Then, if you know delta Ki restricted on the boundary, then you know the gradient parallel of delta key I. Because, you know delta key I, you move along the tangent plane, and you know how it is varying, okay? But if you know delta key I restricted on the boundary of C star, you do not know anything about grad normal delta key I. You know what you can do? You have your boundary C star, okay? You have your delta key I here. You can prolong it along the normal constant, and you get the normal gradient equal to 0. Or you can prolong it in every possible way. Okay, so in a sense here, delta key I and grad normal delta key I are independent quantities. We will go back to this point, but think about this. I can find, given delta key I, infinite prolongations outside the surface delta C star, okay? Each one with a different normal gradient. So you can prolong delta key I, can be prolonged by constant values along the normal. Then grad normal delta key I is 0. Or you can choose any regular grad n delta key I and prolong delta key I correspondingly. I mean, I am here using more or less the words used by Lagrange and Piola in this context. Okay? So first thing is that delta key I and the normal gradient of delta key I are independent quantities. Okay? On the other hand, you can integrate by parts this gradient here on this addend, so that you can get rid of this tangent gradient. Okay? And this is what we will need to do next. Okay, so before, now we open a small parenthesis. We start rediscussing the divergence theorem. Why? Because we need to generalize it to surfaces. Okay, so let us talk a little bit about in R3. So we reconsider another time the divergence theorem, which we already applied. So we have integral over a volume and an integral over the boundary of the volume. Okay, And here we have a vector field W, and we calculate its flux, the area. So this is flux of a vector field through the surface boundary of V. Okay? The genius of Gauss allowed us to transform this flux into a volume integral. So the problem of Gauss was, can I invent an operator? In this moment, I call it a square with a cross, such that this operator applied to W, integrated on the volume, gives us the flux. Okay, now, first thing, here you have an inner product. So this operator must depend on the inner product. So it is something strictly related to the inner product. Okay, so Gauss theorem can be stated as follows. Given the field W, given the Euclidean inner product, to find an operator such that an operator we call like this, such that star holds. Okay. Solution. Choose orthonormal basis in terms of Euclidean inner product. Okay, we call it E1, E2, E3. Okay, then and X1, X2, X3 are the associated coordinates. Then this operator applied to W is equal to the W1, the X1, plus dW2 dx2 plus dW3 dx3. Now look how elegant it is. This is a contravariant component derived, therefore it is a covariant. So we can write this W E d over dx E, or if you prefer W E comma E, if this means the derivative. So And this is called divergence operator. So actually, Gauss theorem tells you that this equality is possible, and integral of div W over a volume, d volume, is equal integral on the boundary of the volume of W and the area. And it gives you the representation of this operator in terms of the components of an orthonormal basis. Okay. Now, what do we need now? Generalization. Okay. Imagine to have a surface. My drawing is very bad, but imagine to have a surface with, this is the surface sigma, and you have the boundary of sigma. The boundary of sigma is a curve gamma. Okay. And you have integral over the boundary of sigma of a vector, a tangent vector Wt, tangent to the surface, dot the outer normal nu. Nu is parallel to sigma, and nu is orthogonal to gamma. So my drawing is not very good, but imagine to have, I am telling you that nu is parallel to sigma. So it is in the nu is tangent to sigma, and nu is orthogonal to gamma. Okay? And now what we want? We want to find an operator such that this integral over dl, so this is a line integral, is equal to this on the surface. So it is exactly the same logical process, but instead of having a volume and its boundary, we have a surface and its boundary. And instead of having tangent to the surface. Okay. By the way, this, and we end, these concepts are the basis of differential geometry, by the way, invented by Ricci, Levi-Civita, continuators of Riemann. So here the Italian school gave a strong contribution. And general relativity. By the way, it is not a case that the only available book about second gradient continua outside Piola and a small group of mechanicians you find in general relativity. Because Einstein proposed a first gradient relativity, general relativity model, but he admitted the logical possibility that it could be a second gradient theory. So he kept this door open for future development. So it is rather amusing that I studied some of these concepts when studying general relativity. Okay, so what we will do next, we will find this cross operator on the surface, and we will go, remark that this boundary is a curve. Okay? So the integration by parts will produce integrals on a curve. Okay? So let's go a moment back to our first formula here, to this formula. If I integrate by parts this animal and this nabla parallel goes to the other factors in this formula, it will let delta ki free. So after an integration by parts, I will get an expression of work as line integral, and you will have something multiplied delta ki. What is something that multiplied a virtual displacement gives you a work? Line force. Okay, so we are now understanding why in second gradient materials you can have line forces, and why in first gradient material you cannot have line forces. In first gradient material, you don't have gradients on the surface, on the boundary, so your integration by part process ends, and you have only forces per unit area. While in second gradient materials, you have gradients on the surface, and integrating by parts another time, you get forces on lines. Okay, but this will need a greater detail and a longer discussion, so we will do it in the next lectures. Okay, I think it is enough for today. Otherwise, I tell you too many things. Alessandro, you can stop the recording.